Okay, so quickly we had those definitions x n. I am writing even though this clear cut repetition, but I have to refer to them time and again. This was this. Then you have seen one thing that z to the power minus k x n was what 0 0 0 and then x 0 up to x n minus k, which we saw yesterday can also be written as 0 z to the power minus k minus 1 x n minus 1, right. This you have seen yesterday, is not it, x n minus 1 vector, on top of it k minus 1 0 and one more 0. Okay. This was the thing, and then we had w k p n was, this is repetition, but this is my workbook. So, I have to write them. K greater than equal to 0 less than equal to p. Okay. This then we defined E p n f forward projection error vector, that is x n to be projected orthogonally on the space spanned by z to the power 1 minus 1 x n up to z to the power minus p x n, past p values at each index n. Those data samples are linearly combined, subtracted from the current data sample error. Those errors are squared, summed with a weighting factor lambda, minimized. Okay. That gives rise to those optimal, minimized means you will get the optimal filter coefficient or predictor coefficient. Then using those coefficients, combine them, you get a vector. There is a projection, take the error, that is the error. That is the meaning of this. So, that was 1 p n. Similarly, we had okay. This is repetition. So, in this context, yesterday we came across one vector p 1 p perpendicular 1 p n perpendicular z to the power minus p plus 1 x n. This we wrote as E tilde, and we said that this would be this. Let us again quickly sum up what was there. Instead of projection, just projection error, consider the projection. This is just recap, but since this is a crucial thing, it will be used again several times today. Forget about the projection error. First, the projection itself. Error means from this vector only you have to subtract this projection. That projection will be what? This guy will be projected orthogonally on the space spanned by z to the power minus 1 x n to z to the power minus p x n. On top of them, the first entry is always 0. First entry of this vector also is 0. So, if you linearly combine this and subtract from this z to the power minus p plus 1 x n, top entry does not give rise to anything. Remaining ones you are finding out the error, each error is squared up, multiplied by a weighting factor lambda, lambda some power of lambda and added and minimized. That is same as though you are considering z to the power minus, I mean it is like this. First column was 0 z to the power minus 1 x n minus 1. Sorry, not z to the power minus 1, just x n minus 1, z to the power minus 0 in fact. Z to the power minus 1 x n, that is 0 and x n minus 1. Then next column was 0 z to the power minus 1 x n minus 1 dot 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 0 dot dot z to the power minus p minus 1. These are the columns, okay. And you are projecting this guy, this fellow. This fellow means there is a 0 on top, in fact p plus 1 zeros, but that you can write as though z to the power minus p x n. So, you are linearly combining them, taking the error, forget about the top entry. That error vector, yes, n minus 1. Thank you, n minus 1. I mean, you are linearly combining them, subtracting from this part, as though the top does not exist, because that does not give rise to any contribution in the overall sum of square errors. Okay, so, you are linearly combining them, subtracting from this, that error vector you are taking up each component, squaring up and adding with a weighting factor and minimizing. That is same as though this is projected, this fellow is projected on the space spanned by this vector up to this vector. If you now see n minus 1, if you call it an index n prime, then x n prime, z inverse x n prime dot 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 z inverse minus, I mean z inverse within bracket p minus 1 x n prime, z inverse p x n prime. So, it is forward prediction error vector, sorry, backward prediction error vector at index n prime, that is we are going back by n prime by p, that is n prime minus p, and looking at p future terms. So, that will be backward prediction error vectors pth order at index n prime. So, that will this entire thing would be what? Pth order backward prediction error at, so I was making this mistake, I mean instead of this it will be better if I put this. Actually, this is what I did not put n minus 1. You could have corrected me. Okay. So, this is clear. This is that n minus 1 means n prime index, backward prediction error, pth order, backward prediction error at n prime index, that vector. Okay. That is what we had. But all these things, and then based on this, we obtain those recursions, you know, E p plus 1 f n was I am not redoing this, this is pretty simple, sigma p n minus 1 b square into E p tilde b. You can take the last component. For the time being, I am not taking the last component, that is pretty simple. And this was, I did this also, isn't it, yesterday? I did for this also. That was minus same delta p n okay. We assume that this is not resulting in division by 0. Quickly, what was the thing? When you go for from E p n f to E p plus 1 n f, basically in that matrix, data matrix, you are adding another extra column z to the power minus p plus 1 x n. I am assuming here that that column does not exist in the space spanned by the previous p fellows, that is z to the power minus 1 x n to z to the power minus p x n. It is not cannot be obtained as a linear combination of that. But I told you also yesterday that is always not always true. If your running index, current index is much less and order is more, I mean this new column could be all 0 column, it is already existing in that space. So, that time the projection error vector will be 0 vector, and as a result this norm square will be 0. We will have this problem. This does not happen in the forward prediction case, because because the columns as such, you know, x 0, x 1, x 2 dot dot dot, and the next one 0, x 0, x 2, 0, x 0, x 1, x 2, then 0, 0, x 2, x 0, x, these columns are linearly independent, isn't it? So, if you go for this quantity, what is this quantity? This cannot be 0, because the first vector x n vector is orthogonally projected on the space spanned by p past vectors, and but x n never lies in the space spanned by those past p vectors, obviously that we have shown, and as a result the error vector is non-zero vector, the norm square is non-zero, but this can happen. So, we have to be careful at least for index n, which is less compared to the order. So, that as you go on order updating and all 0 column emerges, then you have to be careful that this problem comes up. We have to do some manipulation in the algorithm, so that the division by 0 does not take place. Okay. That is a separate story that I will do, and that again requires very smart thinking say later. For the time being, we assume that we are running index, current index is much higher, So, we are not having this problem. Also another thing I said that I am assuming that I have at least one column vector, that is x n, that is as you go back say from recursion p plus 1 to p and p to p minus 1 and p minus 1 to p, you are starting at this point. Okay. What is E 0 n f? I do not know yet. E 1 n f I know. From that, what is E 1 n f? X n projected on the space spanned by Z inverse 1 x n, the error vector. Okay, that is this. But if you put 0 here, then there is a problem, isn't it? X n projected on Z inverse 0 x n and that error and all that, there is a problem actually. Remember, when you say E P n, we start at where the problem is. We start at what is the when I say E P n f, what is the subspace? Subspace spanned by Z inverse 1 x n to Z inverse p x n. If I put a 0 here, it's a, I mean that definition is invalid, because Z inverse 1 x n up to Z inverse 0 x n has no meaning, isn't it? Z inverse 1 x n or Z inverse 1 x n, Z inverse 2 x n or Z inverse 1, Z inverse 2, Z inverse 3, that is fine, but Z inverse 1 x n up to Z inverse minus 0 x n, Z inverse 0 x n, that has no meaning. That is why our limiting case is this. From this recursion directly I do not go for E 0 n f, similarly for backward prediction error. Okay. Here also our starting point is this. All right. So given this, you can find out E 2 f n, E 2 b n and so on and so forth by the recursion, but how to obtain them? Okay. We will see that by clever identification of some vectors as E 0 n f and E 0 n b, we can still maintain the same lattice recursion for the 0th stage also. This is called stage 1 when p equal to 1, when p equal to 0, that will be stage 0, that is the first stage. Now, E 1 f n, what is E 1 f n? Simply, what is E 1 f n? X n projected on Z inverse x n and the error, isn't it? E 1 f n, E 1 f n means what is the subspace? Spanned by Z inverse 1 x n up to Z inverse 1 x n, that is that value only. On that I am projecting x n, taking the error. So, simply x n minus error. So, x n minus inner product x n vector divided by norm square of okay, which you can also write as x n minus Z inverse x n is okay. Here I write separately. What is Z inverse x n? Z inverse x n we all know is 0 x n minus 1, right? And similarly, this recursion we write, this was x n minus 1. This recursion we write. What is this recursion? I know the general definition of E p n b means the vector z to the power minus p x n, that is z to the power minus 1 x n will be projected on the space spanned by z to the power minus 0 x n up to z to the power minus p minus 1 x n. P is 1 here. So, z to the power minus 1 x n will be projected on the space spanned by just z to the power minus 0 x n, because p minus 1, p is 1, p minus 1 is 0. Is that difficult? Space is from z to the power minus 0 to z to the power minus p minus 1, but p is 1, p is 1 here. So, the space is z to the power minus spanned by only z to the power minus 0 x n, that is x n itself, whom I am projecting z to the power minus p x n, p is 1. So, z to the power minus 1 x n, just 1 delayed. So, that means the error vector will be minus inner product between this and x n, which is same as x n, and because they are real, okay. Now, you see, if I make this substitution, if I say that E 0 n f equal to, if I make this assumption, then you see things will be correct. If I put this E 0 is equal to x n, suppose I say this. So, that means E 1 f n, and what is then Z inverse x n? This Z inverse x n is nothing but 0 dot 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 x n minus 1, which is and so this conforms to the form if I assume this. You see, if I define this, what happens to this lattice recursion? X n is immediately E 0 n f p plus 1 p, that is coming. Again delta n, delta p n was what? What is delta p n? Inner product between these two, that is coming. You see, Z inverse 1 x n means 0 x n minus 1, and since x n is E 0 n b, is E 0 n minus 1 b, and by our notation this is this, and this inner product is coming up to be of this form now, between these two, between E 0 n f and this fellow E 0 tilde E 0 n minus 1 tilde b, right, this fellow, this goes here. Okay. Same here also, that E 0 tilde, you see this coming up, E p tilde. So, E 0 tilde, this coming up here. Same here also, E p n f, x n is E 0 n f, and norm square Z inverse 1 x n norm square is simply norm square of this vector is simply norm square of this part. This 0 means nothing. So, this is nothing but norm square at index n minus 1 of the backward prediction error vector at index n minus 1, fine. And x n square means x n is this. So, norm x n square means norm square of this, coming to this form. So, at the 0th stage, this is what you start with. Okay. Then, as you can see here, I already have repeated sigma p say n f square, this is norm x n square, very simple, which is also sigma 0, which is also, by the way, but norm x square means what? What are the elements x 0, x 1 up to x n? We are squaring up the terms, adding, but adding with a weighting factor. What weighting factor? Last one multiplied by 1, last but 1 multiplied by lambda, this way, na? Okay. Now, suppose from this part I take lambda common. I take lambda common from this part. So, lambda times this, do you agree it is a norm square of the vector x n minus 1? So, that means how this can be updated directly in time. This is equal to the same norm square at index n minus 1 multiplied by lambda. Lambda weight brings down the contribution of that previous norm. Lambda times, you can call A for B, does not matter, plus new guy. This is the relation. So, at 0th stage, norm square directly time updated. Each index n, they are recomputed recursively from that previous index value, and using the current data. Previous value, that is the value at the previous index, current data using that they are computed. It is called time update. At 0 stage, you cannot get them back from any previous stage, because that is the starting stage. So, there you are obtaining them in time from previous index value and your current data, putting the two in this formula, you are getting the new value. But such time updating cannot be done for this general sigma p n square, sigma p n f square and sigma p n b square for any stage p. That will be order update. That people have tried, I mean time update equations do not work out, one cannot get. Order updating. Order updating means once I know them, then keeping the index n constant at this index only, from this I will find out sigma 1 n f square, sigma 1 n b square, then sigma 2 n f square, sigma 2 n b square, so on and so forth at the same index n. So, once I do time updating for the 0th stage, get the corresponding values for index n, then at this index n I go ahead by the order update formula for various stages I get the respective values. Mind you, unless I have them, I cannot have this multiplier in the lattice. This is a purely adaptive thing. At every index, the multiplier value changes. So, for pth stage, I first should have obtained this, obtain this, obtain this, obtain this, and then only I can proceed. Sigma p n f square and this fellow can be easily order updated, using the philosophy we did for stochastic lattice. We will just do that. Problem will come with delta p n. This guy cannot be order updated. So, what they do, you then derive a time update formula of this guy at each index n for each order. This cannot be time updated. So, for every stage, I will obtain this from its value of the from its past value. I will not go on, I will not work like this. Okay, for one particular stage, I will do time updating and then go on updating it in order. That is from delta 0 n to delta 1 n to delta 2 n to delta 3 n, not that. But that is not doable. That does not work out. It's not possible to get this kind of relations. So, there for every stage of the lattice at each index n, we will have to compute this directly using some time recursive formula. That is from its past value for a particular p, from its past value, that is delta p n minus 1 will give rise to delta p n. And this you have to do separately for all the stages, no order updating business. For norm square, time updating only at the 0th stage in this manner, and then you go on order updating for the same index n from sigma 0 n f square to sigma 1 n f square to sigma 2 n f square, so on and so forth. So, you first obtain the time order update relation for this norm square, and then I will tackle this. Tackling this will be beautiful linear algebra and not easy, because I will get exact time update relation. So, we have got this quantity sigma p n f square. Just for your sake I am writing down, this is your E p n f norm square, that means inner product with itself, and E p n f means what? P 1 P n, this is your E p n f, comma itself, but then I can drop this projection operator from here by those tricks. You have the same projection operator here followed by x n, but I can drop that operator there. You remember, na? So, simply x n. So, that means, if I have to find out this guy now, sigma p plus 1 n f square, which is this, this is basically we have already found out E p plus 1. For your benefit, I am writing in expanded form, but this is nothing but this, and we already know its order update relation. We know this lattice recursion na, for this. Here we know this lattice recursion. What is this guy? We already know. You can substitute that here. Minus Just have a look, this I am substituting here. Actually, this is absolutely identical to order updating of those prediction error variances we did in stochastic lattice. Procedure is absolutely same. And then xn with this, what is EPFN? EPFN we know, this quantity P1 Pn perpendicular xn, that with xn means I can repeat this operator on xn, and immediately it becomes EPFN with itself. This is what we did that time also, minus these two quantity. So, delta Pn by this remain outside. This with this, what is this guy? I gave you a definition, this guy is nothing but P1 isn't it? What is this guy? In the very beginning today I told you, gave you the definition, I told you I will use it. This is nothing but this case 1 p comma n, 1 comma p comma n, that space you are projecting this fellow. That is why you had a 0 on top and all that, and this E tilde fellow came up. You remember, na? You did in the very beginning today. This would itself be this operator you can again pull on this. So, that will give rise to what? EPFN, EPNF, xn and this P1 Pn perpendicular. Okay. That will give rise to EPNF, and EPNF and this fellow, which is this fellow, their inner product is same old delta Pn. Here there is no difference. We did similar, absolutely similar thing that time also in stochastic lattice. Are you following what I am saying? This operator I will just apply on this, and then I will get EPNF here. EPNF and this total quantity is EPN minus 1 tilde B. They are inner product, both are real. So, it does not matter who is first, who is second. The inner product is delta Pn. Earlier in the stochastic lattice, there become delta P star, because I was dealing with complex valued case in general, and it becomes a star because it has got reverse, and so it become mod delta square and all those there. But here there is nothing like that, because all are real. So, delta Pn square. Once again I am assuming there is no division by 0. Division by 0 comes from the same thing, na? From the same lattice recursion. So, this is an order recursion. Suppose if from the PS stage you already know delta Pn. Important thing is you must know this. Suppose you know this and you know these two norm square for pth order, PS stage, you can find out the same thing for p plus 1 stage. For the forward prediction, in the same manner I can get for the backward prediction, I will do in a minute. This quantity, suppose I just instead of n minus 1, let us start with Pn only. If I know this, I can use it at n plus 1th index, I can store it, because I need it, I need the value at n minus 1th index here, isn't it? So, instead of order updating this quantity where index is n minus 1, let me try with n first. Okay. That means, this value will be stored in memory for usage in n plus 1th index. Let us start with that first. Huh? So, this quantity is what? Norm square of and in case I land into difficulty, then I will switch over to minus n minus 1. Let me try with this first. This is a quantity. X n with itself, but here I drop this operator s. I can do that, this quantity with itself, but then here I drop this operator, and this quantity is what by our definition? Backward prediction error no? Starting at 0th up to pth, z minus 0 x n to z minus p x n. On that space, the space spanned by them, you are projecting this guy, taking the error. So, this is directly this comma x n, and I already have obtained the backward this formula for this recursion. So, I will just substitute that there. Absolutely similar procedure, this is pretty routine. And between these two, what was this quantity? You remember, this was P 1, P n. I gave the definition of this tilde today again for as repetition in the morning. You have to start at 1, go up to P, all of 0 on top. This quantity, between this quantity and x n, I repeat the operator, this bring the operator on x n, immediately I get back. Just a minute. Oh, here I get just a minute. Yeah, here I will have Z2. Sorry, thank you very much. I am doing first, so yeah. Thank you. So, this operator I bring back on this. Thank you very much. Yeah. The moment I bring back this operator on this, I get the same the tilde term here also. This is this thing, this operator I apply on this fellow, Same E tilde P n minus 1 b would come there, and inner product with itself. So, norm square, and that norm square is same as minus this remains as it is into between these two. What is EPNF? EPNF is P 1 P n perpendicular x n, that I will apply on this. So, again the tilde will come up, and inner product between EPNF and that this tilde term, which is again delta P n. So, we will get delta P n square. Not understanding? This is very simple, pretty simple. Okay. So, this is the order update relation. Mind you, I am updating the guy at index n, but in the lattice recursion I need the same fellow for index not index n, but n minus 1. So, that means whatever I compute for index n, that needs to be held in memory for use at n plus 1th index. Similarly, what was computed at n minus 1th index, that was held in memory and now being used in this recursion at index n. So, you need a layer of memory, okay, for holding this order updated value for only this fellow sigma p b square. Whatever you obtain for current index, this needs to be stored, because lattice recursion needs them for the past index, not current index. Here it is fine, but for not for this norm square. So, you need to store. Okay. So, order updating is fine. Past means also when you switch on the algorithm, you have to give initial condition for these fellows. At n equal to 0 you are starting, so at n equal to minus 1 what value it had, you have to give initial conditions, and there I will inject something carefully, so that never division by 0 occurs anywhere. That is separate story, but you understand this philosophy, that since it depends on past value, whenever I switch on the algorithm, I have to give the initial value for this. Similarly, for the 0th stage, wherever there is time recursion, I have to give the initial value. For the 0th stage, there is a time recursion today. That is current norm square was using previous norm square multiplied by lambda plus square of the current term. You remember this thing, na? So, here again for this also I have to give initial conditions, because there is a time recursion. Any time recursion means when I am obtaining current index value from previous index value, I have to give initial condition, isn't it. So, here I need for this, whether it is A or B does not matter, and for every stage I need only for the backward, for norm square for the backward projection error vector. Okay. Now comes this delta fellow, that is the most difficult case. Delta, you know, is the inner product between those two quantities, E p n f and E p tilde E tilde p n minus 1 b, those two fellows. That is, separately, our biggest story is with this guy. In terms of projection, this is P 1 P n perpendicular x n. Here also space is same, most importantly space is same, but vectors are different. This guy, and you know, people tried various ways. Order recursion is not possible here, people could not find out, but they can find out a time recursion, that is delta p n to be obtained from delta p n minus 1 and some expression and all. Not so easily, but at least time recursive, delta p n to be obtained for each p, delta p n to be obtained from delta p n minus 1, separate time recursion, because other order recursion is not possible, people found out. We have to calculate the time recursion. Before I do that, let us do, because that will not be possible entirely today, let us do something. I will be considering a general result now. Suppose I have got a set of vectors u 1 n, u 2 n, dot u l n, l number of vectors, and each of the vector starts at what, n equal to 0, u 1 0, u 1 1, u 1 2 up to u 1 n, that is u 1 n vector. I am not writing it out, I hope you understand this. You already know the pattern of this formula for x n vector, or if you want, for your sake, let me write down. This is what? Data at 0th index, data at 1th index, data at nth index. K could be 1 to L, right? You form a matrix called U n. And suppose there is an external vector d n. Also, let W n be the column space of U n. That is simple, that is space spanned by these columns. Instead of writing span of these vectors, I will say column space spanned by this. Corresponding P n perpendicular orthogonal projection operator and orthoproj error operator for W n, fine. P n d n, what is the projection on the space spanned by this guy, the column space of this matrix, and P n minus 1 d n minus 1. How are these two related? Can I find a relation between them, these two projections? That is the thing, it is not easy, it does not come up so easily. You understand that suppose I started counting time, n equal to 0 done, n equal to 1 done, I stopped at n equal to n minus 1. I got a data matrix. That matrix column space, I am projecting d n minus 1 vector on that, getting a projection. Now, you introduce the data, current data u 1 n, u 2 n, u l n for each of the columns. So, your data matrix gets one extra row. New column vectors, they span a space, on that I project d n orthogonally, I get p n d n. Obviously, the entire vector is new, because I got a new set of linear combiner coefficients now, but how are they related? It is not easy. It is not easy. You remember I defined that pinning vector pi n 0 0 0 0 0, only last guy is 1. Okay. Consider a figure that suppose instead of so many columns I just have only one column, u 1, only u 1 fellow. Suppose I have a vector u 1 n minus 1 and a 0, like this same. So, 0 I put, and the vector pi n will be what? 0 0 0 here and 1 here. You understand those two will be orthogonal to each other, pi n and these two. So, that means pi n could be like this, 90 degree, this is pi n, and consider the vector u 1 n. What is u 1 n? U 1 n is this guy plus the latest component. And u 1 n, isn't it? This fellow plus the latest component. That will be somewhere here, u 1 n. Okay. In fact, I should have made it 90 degree, I do not know, if let's take it as 90 degree. Okay. You can see one thing, u 1 n is simply a linear combination of these two. What is u 1 n? This part is common, last guy is u 1 n scalar, and here last guy is 1. So, if I take this and multiply this by this last scalar fellow, add, I will get this last scalar fellow. If I take this, multiply pi n by that. So, the bottommost entry of pi n will be u 1 n, all other entries on pi n will be zeros, and here I am leaving it as it is, last entry is 0, other entries are this, and add that 2, you get this, isn't it? That means the space spanned by pi n and this fellow, that is included, that is subset of, that is subspace of the space spanned by pi n and this fellow, because this is a linear combination of these two. So, the space spanned by pi n and this, that is a subspace of, or that is contained in the space spanned by pi n and this. Alternatively, I say that this guy again is a linear combination of these two. How to get this guy from these two? Take last fellow, reverse the sign, minus, multiply pi n by this minus u 1 n, add the 2. So, last entry will cancel, you get the 0 fellow. That means, the space spanned by this and this, pi n and this, is contained in the space spanned by pi n and this, because this is a linear combination of these two. That means, space spanned by pi n and u 1 n is same as the space spanned by pi n and this, but pi n and these are orthogonal. So, if on the same space I want to project somebody, instead of viewing the space as though it is spanned by these two fellows, I can view it as though it is spanned by these two fellows, which are orthogonal. So, that projection will be what? Summation of projection on this axis and projection on this axis. Please see already one thing, I have already got a data vector of the past. My purpose is to relate past projection with the current projection. I already got one data vector, already I have taken the case of only one column vector, I could easily explain it to my, I have already brought in a column vector which is the past column vector, past data vector. Okay. But one thing is sure, that any external vector projected on the space spanned by pi n and this u 1 n is same as the projection space, the projection on the space spanned by pi n and this, because the two spaces are same. But when you take that external vector projected on the space spanned by pi n and this, it will be summation of projection here and here. Now, what is the projection of any fellow on pi n? Only the last component, isn't it? other integer multiplied by 0, last component into 1 multiplied by 1, no lambda. So, last component, and similarly that external vector d n projected on this will be what? D n and this inner product between d n and this. Last entry you forget, is not it? Other entries will be multiplied. D n will be what? A vector like this, d n minus 1 vector and d n. So, d n and 0 will cancel in the inner product, and you have to take this guy and this guy. Lambda will come up. But when you take the inner product, last two entries multiplied with 0, fine, but last but one entry, there a lambda will come up. Take lambda common, lambda square up to lambda to the power n. So, lambda common. So, if you take one lambda common, it will simply the inner product between this guy and this guy, is not it? So, that means what is the overall projection? Projection on this, I will be doing it elaborately, but I am just telling you this is just through this figure I am giving you here. What is the projection of the d n vector on this space? One is the projection on this pi n fellow, which is 0, 0 vector and only a scalar d n. And what is the projection on this? That is projection on this d n minus 1, you are doing inner product of this, what are we doing? What is the projection of orthogonal projection of d n vector on this? D n inner product with this divided by norm square of this into this, is not it? That inner product, last guy goes, remaining inner product is lambda times the inner product between d n minus 1 vector and e 1 n minus 1 vector, divided by norm square of this fellow. Norm square of this fellow will be what? Lambda times the norm square, okay, into this fellow, all right. Lambda will cancel there. So, that means as though, so the projection last component is 0, you are projecting means you are taking the inner product divided by norm square into this guy. So, last component is 0, this guy multiplied by a constant, is not it? Let me do it here for your sake, 0 d n, and you have to project this on this. You have to project this on this. What I am saying is this, that projection will consist of what? This vector first, this vector multiplied by constant. What is that constant? Inner product between these two divided by norm square of that. Lambda will cancel, you have seen. Inner product between these two means what? Lambda times inner product between this and this. Norm square means norm square of this ratio. So, isn't it what you get when you are doing the same projection at n minus 1th index, as though d n minus 1 vector was to be projected on u 1 n minus 1 vector, isn't it? So, you get that term, that is d n minus 1 vector inner product u 1 n minus 1 divided by the norm square of u n minus 1 into u 1 n minus 1. So, basically this is an estimate at index n minus 1. Estimate means d n minus 1 if projected orthogonally on this vector, that is u 1 n minus 1, what you get is this and then 0. You understand this? Tomorrow, next time I will repeat this again, but I am just telling you, have you understood this part? Inner product between this, I am projecting d n on the this axis. So, I have to take this orthogonal, I mean this vector as it is, this 0 is this 0 as it is, and this will be multiplied by the inner product between the two divided by norm square. Lambda will cancel, inner product last entry disappears. Since lambda cancels, it is simply the inner product between these two guys divided by the norm square of this guy. That times this u 1 n minus 1 here. That is nothing but projection of d n minus 1 vector on u 1 n minus 1 vector. That is an estimate based on data up to n minus 1 along this axis. This 0. This is the overall projection. So, what is the overall projection error? This summation has to be subtracted from d n vector, and immediately this guy will disappear, is not it? And d n minus 1, this what is the error? Error will be, if you call error will be d n minus the summation. Summation is what? Last guy goes, and on d n is what? Na? D n minus 1 vector, and then d n cancels. D n minus 1 vector minus is estimate. That is the error. That is error. Which error? D n minus the d n minus 1 minus the projection on these axes. That error, not on the overall projection. Okay. This relation we will be using in a more generalized from the next class. You will see how it comes there actually. This I just drew a diagram. I will again start from here. Just come prepared with this little bit. This is not easy, but very interesting. Okay then. Thank you very much.